Hi everybody, this is the sixth video. It covers exercise 11, and this is the first problem, which isn't simply an abstract problem. This one, at least in principle, could come from the real world. It asks you start with a rectangular solid of volume 1,000 cubic meters and to find the dimensions that will minimize the surface area. So let's set this up by first drawing a picture. So this will be our rectangular solid, and I've given names to the side lengths, x, y for the bottom of this box, if you like, and z for the height. And the problem tells us that the volume is 1,000 cubic meters, and we know that the volume of a box is given by multiplying the base, the width, and the height, so x times y times z. So multiplying these, we get 1,000. Now, what we're trying to do is minimize the surface area. So how do we get the surface area? Well, okay, there are 6 sides to this box that make up the surface, and each one will have area equal to the product of the length and width of the sides. So for instance, this bottom bit of the rectangle, or this bottom rectangle will have area x times y. And of course there's 2 of those. There's this one on the bottom and there's this one on the top. So the surface area from those 2 sides will be 2xy. There's also this front piece and the corresponding back piece, and the lengths of those sides are x and z, so you'll get 2xz's, and then you have these 2 side pieces, this one over here and this one over here, and those lengths are y and z, so you get 2yz. So in total, the surface area will be 2xy plus 2xz plus 2yz. And it looks like we have a function of 3 variables. But if we look back at this original equality, this tells us we can actually write z in terms of x and y. In particular, z is 1,000 divided by xy. So actually in our surface area formula, we can go through and get rid of z everywhere we see it. So if we do that, we'll end up with 2xy plus 2x times 1,000 over xy plus 2y times 1,000 over xy. And, well, you see there's a little cancellation we can do. We can multiply 2 by 1,000. And if we do that, we end up with 2xy plus 2,000 over y plus 2,000 over x. Alright, so our goal is to minimize this function, s, which gives us the surface area. And it's really now the same problem that we've been solving all along. Okay, so minimize a function of 2 variables given in the following way. We're going to look for the gradient, say. So the gradient's given by 2y minus 2,000 over x squared in the x direction, and in the y direction it's 2x minus 2,000 over y squared. The similarity, of course, comes because our function s of xy is completely symmetric in x and y. Alright, well, we would like to know where the gradient is equal to 0. Well, that's going to be when each component is 0, and, well, if we combine these into fractions, one fraction, we get these two expressions equal to 0. And, of course, to get fractions equal to 0, we make the numerators equal to 0. So let's see, what will that give us? Well, you see, the top one's going to tell us that 2x squared y minus 2,000 is 0, or if you like, 2x squared y is equal to 2,000. But the bottom one tells you that 2xy squared is equal to 2,000. So those 2 expressions have to be equal to each other. Get rid of the 2's, and you have that x squared y is equal to xy squared. Alright. Now, it could be that one of x or y is 0, but if that was the case, then the gradient wouldn't even be defined. Yeah. So we could have that if x is 0 or y is 0. But of course, that'll give us a critical point, but not where the gradient is 0. And I claim here that the only alternative otherwise is that x is equal to y. And that's true, because if neither of x or y is 0, then you can divide both of these by xy. And if you do that, you'll be left with x equals y. Okay, so it could be that the critical point is 0, 0, but or that one of x or y is 0, but then actually our original box doesn't make any sense. You just aren't going to have a box if you have a side length of 0. So we can exclude those, and all we have to worry about is where x is equal to y. And in that case, well, go back up, say, to the original equality, this was equal to 0. So that would mean if y is equal to x, we have 2x cubed equals 2,000, which tells you x cubed is 1,000, or x is equal to 10, and y was equal to x, so y would also equal 10. Okay, so this tells us that our only relevant critical point is when x and y are both 10. Now, it could be that that's not really a minimum. So how can we check that? Well, of course, we can use our second derivative test. Let's compute the d. So we need our second partial derivatives. In the x direction, we get 4,000 over x cubed. Okay, our second partial derivatives in the y's will be 4,000 over y cubed. Of course, this was symmetric in x and y, so that's no surprise. And if we first do the x's and then the y's, we end up with 2. Okay, so at our point 10, 10, let's see what happens. Well, 10 cubed would be 1,000, so this will give us a 4. Again, 10 cubed is 1,000, so this gives us 4. So 4 times 4 is 16, and we subtract 2 squared, which is 4. 16 minus 4 is 12. Since d is positive, we have to look now at the sxx term. Okay, when x is 10, we saw this was equal to 4, which is positive, so in fact we get a local minimum. And that tells us that setting x equal to y equal to 10 really will minimize the surface area of the box. If you want to look at videos for one of the other exercises, you can click one of the links here.